Welcome back, everybody. Today we're going to talk about oxidation numbers. All right, so pretty simple topic. We really just have two things to talk about. We want to talk about what oxidation numbers are and why they're important, and then we'll talk about how to determine oxidation numbers for a particular element in a compound. And to do that, for this part, we're going to have a bunch of rules. There are a lot of rules, but they're all pretty simple. So we'll do that and then we'll practice a little bit. All right, so let's take a look at oxidation numbers. All right, so we've seen before some chemical reactions in which electrons are transferred from one species to another. This is a really common one. It shows up in a lot of labs. Okay. And we can tell that electrons are being transferred because the copper over here on the left side has a charge of +2, and the copper over here has a charge of 0. So the charge on the copper is decreasing. It must be gaining electrons, right? And this process, remember there was a brief section on electron transfer processes or redox processes in the first semester, so that we know that when an element gains electrons and its charge decreases, that's called a reduction. Okay. Now, zinc, on the other hand, is going from a charge of 0 to a charge of +2. And if the charge is increasing, it must be losing electrons. And we know that losing electrons is called oxidation. And if we have a reaction in which, well, I was going to say, if we have a reaction in which both of those processes are happening, but really you can't have one without the other. A reduction process is gaining electrons, they've got to come from somewhere, and an oxidation process is losing electrons, they've got to go somewhere. So these two things always occur together. And when they occur together, we call that a redox reaction, right? Redox is a combination of reduction and oxidation. Okay, so this is all just kind of a bit of a background reminder thing. So when we're talking about redox reactions, in order to see the transfer of electrons or keep track of the transfer of electrons, we need to have these charges here so that we can tell who's gaining electrons and who's losing electrons. In this particular case, it's really easy because the copper and the zinc have charges of 2+ in their ionic states, and they have a charge of 0 in their metallic state. So it's really easy to see when things are gaining and losing electrons. Where oxidation numbers become important is in more complicated processes, which are actually more common than these simple ones. A lot of different cases of reactions in which electrons are being transferred, but sometimes it's not quite so easy to see what's being transferred. And so if we look at a case like, it's not a good color choice. Permanganate going to manganese 2 ions. Right? This is also a reduction process, and the manganese here is gaining electrons. But it's difficult to tell that because these numbers here um, aren't quite as easy to read as they were in the case for monatomic ions. And the reason is because we've got this polyatomic ion here, this permanganate ion. That makes it a little bit more complicated. Okay. So what oxidation numbers is oxidation numbers are a way to keep track of which species are being oxidized and reduced in a reaction when the charges are made more complicated by the case of neutral molecules and polyatomic ions. Okay. And one way to think of this is okay. So we'll say two things about this. Oxidation numbers are just kind of a bookkeeping device for keeping track of electrons in more complex redox reactions. Okay, so that's one way to think of it. That's one of the reasons that oxidation numbers are important. Um, Another thing we could say about them um, is when we've got simple ions everywhere, oxidation numbers are obvious. They become less obvious when we involve covalent bonding. So oxidation numbers That's a C there. Okay. So another way to define oxidation numbers is that oxidation numbers are the effective charges on each atom that would exist if all of the bonding were completely ionic. Okay. Uh, in reality, it's not. Most of these bonds are sort of polar covalent. They've got some ionic character, but there's a lot of electron sharing there. Okay. So oxidation numbers in that sense are sort of a little bit of a fiction, but they're important in helpful in keeping track of electrons, and you know which atoms are holding excess electrons, which atoms are electron deficient, and you can kind of predict which way the electrons are likely to move in a reaction based on these oxidation numbers. All right, so let's take a look at how to determine oxidation numbers. All right, we've got 7 rules. A lot of them are really simple. This is a simple one. Uh, a neutral element by itself has an oxidation number of 0. Okay, so if we have sodium, then its oxidation number is just going to be 0. Okay, if we have iron, its oxidation number is 0. Okay, it can be gases, right? So if we had, this is a little bit of a odd example because neon doesn't really participate in bonding, so it's not really going to show up in any redox reactions. But the oxidation number here would still be 0, right? It can be, it doesn't have to be monatomic. You can have something like hydrogen, right? As long as it's an element by itself and it doesn't have a charge, then its oxidation number is still 0. Same would be true of oxygen, right? And it doesn't matter what form it is. Oxygen can be O2. You can also have ozone. Still be 0, right? Bromine is a diatomic liquid. Its oxidation number is 0. Okay. So as long as it doesn't have a charge, and as long as it's not in a compound with something else, all right, its oxidation number is going to be 0. All right, that's pretty simple. All right. Next one's also simple. This goes back to what we were looking at initially when we were looking at simple redox reactions with the copper and the zinc. And that is for any monatomic ion, that means just one atom with a charge, the oxidation state is the same as the charge. All right? So, for example, that copper 2 plus, its oxidation number is +2. We had in that example, we had zinc 2 plus, its oxidation number is +2. We often have sodium with a positive charge, that would be +1. Right? Iron can exist as a +3 iron, excuse me, +3 ion. So of course that would be +3. Okay. Now this is true for both cations and anions. So if we had chloride, this is an anion now, this would have an oxidation number of -1. Fluoride also -1. Sulfide be -2. All right. So one way to think about this is if you go back to the definition I just gave you about oxidation numbers, the oxidation number is the charge that would exist if all of the bonding was ionic, right? And in cases like this, the bonding really is ionic because you've just got single monatomic cations and anions. So the oxidation number is just going to be the same as the charge. Okay. Okay, so here's where it gets a little bit interesting. For things with more than one atom or more than one element in the same molecule, right? Or polyatomic ions. So this would be for molecules and polyatomic ions. The super duper duper important rule is that the sum of the oxidation numbers must be equal to the net charge. Okay? If you've got a neutral molecule, that means the sum of the oxidation numbers is 0. If you have a polyatomic ion, then the sum of the oxidation numbers is that net charge. Okay. All right. So this means you're going to end up with 2 elements. Let's take an example like sulfur tetrafluoride. Okay. So this is a neutral molecule. We know that the sum of the oxidation numbers has to be equal to the net charge. Since it's neutral, the net charge is 0. Okay. So I'm going to set up a little algebraic equation here, setting these oxidation numbers equal to 0. So I'm going to use S for the oxidation number on sulfur and F for the oxidation number on fluorine. But notice we've got 4 of those. So I'm going to put a 4 here. This is equal to the net charge, which is 0. Okay. So we would read this, the oxidation number on sulfur plus 4 times the oxidation number on fluorine has to equal the net charge, which in this case is 0. Okay. So now we've got 2 unknowns, the sulfur and the fluorine. We don't know the oxidation numbers on either of those. So now we go down to this second rule here. And the second rule is whichever element is most electronegative, it gets its preferred anionic charge. Okay. So if you look at the periodic table, you see fluorine is furthest to the top right. In fact, fluorine is the most electronegative element in the table. So fluorine is going to get the charge that it wants. And when fluorine is an anion, it has a charge of -1. So we're going to give fluorine its preferred charge of -1. And sulfur, oops, that's still equal to 0. And sulfur will be our unknown. We don't know what the charge is on sulfur. Okay. But now we have an equation with just one variable. So we can say sulfur, will multiply this through sulfur -4 equals 0. So then we get sulfur equals +4. Okay. So that means the oxidation on sulfur is +4, and the oxidation number on fluorine is -1. Okay. Let's try another quick example. Okay, this time we'll do a polyatomic ion. And we're doing chlorine, so let's choose green. It's a good color for chlorine. All right, so this is the chlorite ion. We've got chlorine and oxygen. So we can start with an algebraic relationship. Okay, we know that the oxidation number on chlorine plus 2 times the oxidation number of oxygen. And I'm going to do something here. Whenever I write oxygen in an equation like this, I'm going to put OX instead of just O. I know that the atomic symbol is O, but if you just write O, it can look like a 0. So I'm going to write OX for oxygen here. Oxidation number on chlorine plus 2 times the oxidation number of oxygen has to equal the net charge. The net charge in this case, because we've got an ion here, the net charge is -1. Right. Then we go to the periodic table to see which one is most electronegative. And chlorine and oxygen are both very close to fluorine. They're both 1 away. So this is kind of a special case you probably need to know. It comes up fairly often, oxygen and chlorine together. Oxygen is more electronegative than chlorine. Okay, when you've got things on a diagonal like that, and they're both the same distance away from fluorine, the one that is in row 2, boron, carbon, nitrogen, oxygen, fluorine, those are always more electronegative than the other ones on their diagonal rows. Okay, so oxygen is more electronegative than chlorine. That means we're going to give oxygen its preferred anionic charge. Chlorine is going to remain a variable. Okay. Oxygen's preferred charge, if it were an ion all by itself, oxygen would be -2. That's because of its position in the periodic table. And so that's all going to equal -1. Now we just have to solve this algebraically. We get chlorine -4 equals -1. I'm going to add 4 to both sides. And we get chlorine equals +3. Okay. So that tells us that in the chlorite ion, chlorine has an oxidation number of +3, and oxygen has an oxidation number of -2. Okay. All right, oxygen. We just saw an oxygen there. Oxygen can be a little bit complicated. So we've got a bunch of rules for this. Most of them are really simple and make perfect sense. First one is, as a neutral element, its oxidation number is 0. That's pretty obvious. That just goes back to, I think it was our first rule, right? So for something like O2, the oxidation number is just is just 0. Okay, oxidation number is 0 for oxygen, right, in its elemental state. Okay, if it's a monatomic anion, its oxidation number is -2. So if we have something like barium oxide or potassium oxide, these are all ionic compounds in which you have an oxide ion, and that oxide ion has a -2 charge, so therefore the oxidation number is just -2. So you should recognize those from ionic nomenclature back in the first semester. All right, this is helpful. In nearly all of its compounds, its oxidation number is -2. Okay, so if it's an ionic compound, then it's -2. But also, if it's in something like sulfur trioxide or NOCl or water, so on and so forth. In almost everything, it's -2. And that, again, that really kind of goes back to the rule that we just had, right? The most electronegative element in a compound gets its preferred negative charge. And oxygen is almost always going to be the most electronegative element. The only time it's not is if you had a compound with fluorine and oxygen. This compound does exist, but it's extremely rare, so we won't worry about this one. In that case, you'd have to give the preferred negative charge to fluorine and then use algebra to figure out what charge you end up with on the oxygen. Okay? But in every other case, oxygen gets its preferred negative charge, which is -2. Okay. All right. The only common exception to that is peroxides. And in peroxides, the oxidation number of oxygen is -1. Okay. There's one fairly common peroxide that, of course, is hydrogen peroxide, right? Okay. And in hydrogen peroxide, oxygen has an oxidation number, of -1 instead of -2. And the hydrogen has an oxidation number of +1. There are some other peroxides like sodium peroxide. Those are fairly rare, but they are out there. You might see them in some of the problems in the textbook, or rarely you might see them on a quiz or a test. This one, however, hydrogen peroxide, this is pretty common, so there's a decent chance that you'll see that one. All right. So just remember that for peroxides, the oxidation number of oxygen is -1 instead of -2. All right, and that brings us to hydrogen, which is the other element that behaves a little bit funny at times. First rule, as a neutral element, oxygen is always 0. Again, that's just the first rule, right? So if we got H2 in the element, the oxidation number is 0. Okay. If it's an ion, then the oxidation number is the same as the charge. That is, I think that was probably our second rule, right? The difference is, the thing that's weird about this one is that hydrogen can have two different ions. 95% of the time, almost all the time, it's this one, which is called the hydrogen ion, right? And that's +1. Occasionally, you come across the hydride ion, which is -1. Okay. If it's by itself in a solution, in fact, you'll see this a lot in a chemical reaction, then clearly that's going to be hydrogen plus, and so it would be +1, right? If you had hydride like that, then of course that would be -1. Hydride generally is not stable in solution. Usually you'll see hydrides as part of a solid compound rather than floating around by itself. But in any case, main point is there are two different ionic forms of hydrogen. Hydrogen, which is +1, and hydride, which is -1. Okay. Now, when it's in a compound, it can be either +1 or -1. And the way to tell, again, goes back to the other rules that we've already talked about. The most electronegative element gets its preferred anionic charge. Now for hydrogen, hydrogen is odd. If you look at the periodic table and you look at tables of electronegativity, hydrogen, we usually use the periodic table to determine electronegativity. As you move to the right, electronegativity increases. And hydrogen is kind of an outlier. It's way over there by itself on the far left-hand side. But for the purposes of electronegativity, hydrogen fits right in here between boron and carbon. Okay. So for all of the nonmetals out here, hydrogen is more electropositive. The nonmetal is more electronegative, so the nonmetal is going to get its preferred charge. Okay. If, however, hydrogen is bonding with something over here, which are the metals, and down here, the metalloids, then the hydrogen is going to be the most electronegative. And so the hydrogen would get its preferred anionic charge, which is -2. Okay, so let me put that rule up here. All right, so when bound to nonmetals, that means everything on the far right-hand side, hydrogen is more electropositive, and it has a +1 charge. The nonmetal is more electronegative. It gets its preferred anionic charge. Okay. When bound to metalloids or to metals, hydrogen is more electronegative, and it's -1. Okay. So, for example, if we had something like hydrochloric acid, okay, chlorine is a nonmetal, so it is the most electronegative element in the compound. It's going to get its preferred negative charge, which in this case is -1. Hydrogen is more electropositive, so it's going to be +1. Okay. But if we had something like NaH, okay, now this is a metal, so the sodium is the most electropositive. I'm stumbling over my words today. Okay. The hydrogen is the most electronegative, so that means that this must be a hydride, right? And this, in fact, this is called sodium hydride. And in this case, the hydrogen would be -1 and the sodium would be +1. Okay. The same would be true if we had something a little bit more in the middle of the table, something like GaH3. Gallium is a metalloid. Okay. but in this case, hydrogen would be the more electronegative, so this is a hydride, right? This would be called gallium hydride, and the hydrogen would be -1. The gallium, remember that algebra, we're not going to do the whole thing here, but if the net charge is 0, there are 3 hydrogens. That means that the gallium must be +3. Okay. All right. You can generally tell by the way that they're written. We usually write compounds with the most electropositive element first and the more electronegative element second. So when you're looking at things like gallium hydride, sodium hydride, or hydrogen chloride, you can tell by the way that they're written. One other thing that comes up with hydrogen is organic compounds. These are things where the carbon is the most important element. And for organic compounds, we typically write the carbon first, regardless of electronegativity. So in organic compounds like methane or methanol or even benzene, C6H6, and all of these organic compounds, hydrogen is always +1. Okay? So in any organic compound, hydrogen is +1. All right, almost done. 2 more rules. All right, and this is an easy one. In compounds, active metals, that means everything group 1 and 2, alkali metals, alkaline earth metals, always have oxidation numbers of +1 and +2, respectively. So if it's all by itself, again, sodium would have an oxidation number of 0, but if it's in a compound, then sodium would be +1. For group 2 metals, things like magnesium, again, if it's by itself, the oxidation number is 0, but if it's in a compound, like magnesium chloride, then the oxidation number of magnesium is going to be +2. Okay? I can't think of any exceptions to those rules. So everything, all of the metals, I guess we could say hydrogen is an exception, but for the alkali metals, lithium, sodium, potassium, rubidium, cesium, if it's by itself, it's 0. If it's in a compound, it's +1 always. For the alkaline earth metals, beryllium, magnesium, calcium, strontium, barium, if it's by itself, it's 0. If it's in a compound, it's +2 always. Again, I can't think of any exceptions to that. One thing I'll mention about this is if we go back to that example we talked about with peroxides, most of the common peroxides are either hydrogen peroxide or active metal peroxides. And so this is a way that kind of helps you identify peroxides. Let's say you had this. This is actually potassium peroxide. If you didn't recognize this as a peroxide, you would say oxygen is most electronegative. Oxygen is going to get its preferred charge. You'd write your equation out like that, and then you say oxygen gets its preferred charge, which is -2. When you do the math on that, you get potassium equals +2. Okay, but That can't ever happen. Potassium is never going to be +2, right? So if that happens, you know that you've made a mistake. Okay, this is one of the nice things about this. Um, so if you try that and it doesn't work out, same thing is true for hydrogen peroxide for that matter, actually. If you put in the wrong thing for oxygen and hydrogen peroxide, you get the same error. So if you do that and you see, okay, clearly there's a mistake there, then say, well, maybe it's a peroxide, and just give that a try and see if it works. So for peroxides, the oxidation number of oxygen is -1. Right. Okay. So if we assume that oxygen is a peroxide in this case, we get oxidation number on potassium is +1. It's an alkali metal, so that makes perfect sense. So we know we've got it figured out. Okay. All right. That's a way to pick out peroxides. All right. And then the last rule, this isn't something you always have to do, but sometimes if you have a complex molecule, if you've got an ionic compound with both a cation and an anion, it's sometimes helpful to consider those two separately. So if we had something like potassium chromate, okay, then we've got two ways to solve this. One is we could just write out the algebra as it is. 2 times the oxidation number on potassium plus the oxidation number on chromium plus 4 times the oxidation number of oxygen equals 0. And then we put in the things that we know. Potassium is always going to be +1. Chromium we don't know. And oxygen is the most electronegative, so it gets its preferred anionic charge, which is -2, and that's 0. And the whole thing is equal to 0 because it's a neutral molecule. Okay, so if we do the math on this, we end up with 2 plus the oxidation of chromium -8 equals 0. And this gives us chromium -6 equals 0, or chromium equals +6. Okay. All right, so then we can say potassium's got to be +1, chromium +6, and oxygen is -2. All right, that's a perfectly acceptable way to do that problem, but the algebra is a little bit complex. Well, it's really not that complex, but it's a little bit messier than it needs to be. We could simplify this a little bit if we just look at this potassium chromate and say, okay, I recognize these ions. Potassium chromate is a compound composed of potassium ions and chromate ions. All right. In order to balance everything out, we need to have 2 potassiums with 1 chromate. Right? But these are the basic ions that compose potassium chromate, and so therefore we know that the potassium is +1 because this is just an ion by itself. It's just a monatomic ion. Right? Then all we have to do is worry about this chromate here. Right? And so now for the chromate, we can write our algebra this way. The oxidation number on chromium plus 4 times the oxidation number of oxygen equals -2. So chromium, let's do this. And oxygen, again, because it's most electronegative, it gets its preferred charge of -2. So this gives us chromium -8 equals -2, or chromium equals +6. We end up at the same place doing it this way, but the algebra is a little bit simpler if we look at that polyatomic ion all by itself instead of looking at all three elements simultaneously. It's your choice. You can do it either way. All right. So what I'd like to do now is just do a couple of examples. I think I've got 9 of these. For each one of these, when we get the set of examples, go ahead and pause the video, work out the oxidation numbers for each of the elements on your own, and then unpause it, and we'll look at it together. Okay, so this is pretty simple, right? This goes by our second rule, I think. Any monatomic ion, the charge or the oxidation number is just the same as the charge. So in this case, the oxidation number for copper is just +2, just that simple. Okay. For this next one, we've got 2 that we don't know, carbon and oxygen. So we'll use our algebra here. Oxidation number on carbon plus 2 times the oxidation number of oxygen equals 0 because it's a neutral molecule, right? If there's no charge up there, we know that it's neutral. The whole thing has to add up to 0. We look to see which element is more electronegative. Oxygen is more electronegative, so it gets its preferred anionic charge of -2. And so we get carbon equals +4. Okay. Remember, one of our rules for oxygen was that it's almost always -2. I think you're probably starting to see that that happen. It's -2 almost all the time. All right, and then for pH 3, we do the same thing. Set up our algebra. Again, neutral molecule, so the net charge, sum of the oxidation numbers is 0. Which one is more electronegative here? Since we've got a non-metal here, phosphorus is a non-metal, that one is going to be the more electronegative. It gets its preferred charge, which if you look at the periodic table, that's going to be -3. And hydrogen, in this case, we know hydrogen, I'll go ahead and put an H in here. Okay, but we knew that hydrogen was going to be +1, right? Hydrogen's either +1 or -1, and it's +1 anytime it's bonding to nonmetals like phosphorus, right? So we could just put in +1 for hydrogen and then solve for phosphorus. We could have done that either way around. Either way, we'd get the same thing. Phosphorus is +3. Excuse me. Phosphorus is -3, and the hydrogen is +1. Okay. All right. Okay. Same thing here. Give these a try, and then unpause, and we'll compare our results. Okay. This is back to our, I think, our very first rule. Any element by itself, the oxidation number is 0. So that one's simple. Okay. Now we'll look at the chlorate ion. This is similar to one of the examples we did with chlorite, but in this case it's chlorate. So the oxidation number on chlorine plus 3 times the oxidation number of oxygen has to equal the net charge, which in this case is -1, of chlorine and oxygen. oxygen is more electronegative, so it gets its preferred anionic charge of -2. And then if we do the algebra, we see that chlorine is +5. So chlorine has an oxidation number of +5, and oxygen is -2. All right, for PF6, this is the hexafluorophosphate ion. Not terribly common. We can start our algebraic equation like that. The most electronegative element in this compound is fluorine. So the fluorine is going to get its preferred anionic charge, which is -1. And that gives us +5 for the phosphorus. So in this compound, phosphorus has a charge of +5, and fluorine has a charge of -1. All right, 3 more. All right, take a crack at these guys, and then we'll compare our results. Okay, this is the dichromate ion, similar to the chromate ion that we had before, except for now we've got 2 chromiums. So we set up our algebra. 2 chromiums plus 7 oxygens equals the net charge, which is -2. Oxygen is most electronegative, so it gets its preferred anionic charge of -2. 2 chromiums -14 is -2. So when we get to the end of our algebra, chromium has an oxidation number of +6. And oxygen, once again, is -2. All right. Next one is barium hydride. This has a hydrogen in it, which again can be a little bit tricky. But one, if we don't know what the hydrogen is, we can just look at the barium. Anytime an alkaline earth metal, a group 2 metal, anytime it's in a compound, it's going to be +2. So we could just put in a +2 and solve for hydrogen. Or we could look at this and recognize whenever hydrogen is bonding to a metal, the hydrogen is going to be the more electronegative. And so instead of a hydrogen +1 ion, we recognize that this is a hydride compound composed of the H- hydride ion. So the barium would be +2 and the hydrogen would be -1. You can do the algebra on that too, but really we can use our rules to determine the charge of both the barium and the hydrogen without resorting to the algebra. So you can do that whichever way you'd like. All right, now the last one is sodium sulfate. I have accidentally jumped ahead. Okay. All right, so let's do our sodium sulfate here. All right. We've got 2 things we don't know. Oxygen is most electronegative, so it's going to get its preferred anionic charge of -2. We know what that one is straight off the bat. But that leaves us with 2 other things, sodium and sulfur. We can solve this 2 different ways. We can say we can write a long or longer algebraic equation like this and say, because sodium is a group 1, we know that it's going to have a charge of +1. Sulfur, we don't know. Oxygen is the most electronegative, so it's going to get its charge of -2. Oops, I got a little mistake there. I think you probably noticed that already. I put a 2 here, but I need to look more carefully. That's a 4, all right? All right, so our algebra would be 2 times the oxidation number of sodium plus the oxidation number of sulfur plus 4 times the oxidation number of oxygen. Sorry about that. Equals 0. Put a 4 there. And then if we do the algebra on that, we end up with sulfur equals +6. Okay, but we could do that in a simpler way, as long as we're paying attention, don't put the wrong number in for oxygen. We can recognize that this compound is sodium sulfate, and sodium sulfate is composed of sodium ions and sulfate ions. And the sodium ions are just have a +1 charge, so the sodium is going to be +1. Again, anytime sodium is in a compound, it's going to be +1. And then when we do the algebra, we really only need to worry about the sulfate. That allows us to make a slightly simpler equation. The oxygen still gets a charge of -2. Oops. So you end up with a +6 for sulfur. So +1 for sodium, +6 for sulfur, and -2 for oxygen. All right, that's what I meant to put on the last slide, but I do weird stuff with my pen sometimes, and I don't know how I do it, but sometimes I accidentally advance the slide when I'm trying to write or erase or something. Anyway, after we've done that, we would have arrived here on our last slide. Our summary slide. So in this video, we talked about oxidation numbers. We talked about what they were used for. And again, there are 2 ways you can think about them. One is they're kind of a bookkeeping device for keeping track of electrons in redox equations. And 2, they're a way of assigning charges as if all of the bonding were ionic. When you've got ionic charges, it's really easy to count electrons and figure out who's being oxidized and who's being reduced. For things with polyatomic ions and molecules, it's more complicated. So this is a way of treating those as if they were ionic so that we can assign charges to all of the different atoms and keep track of the electrons. And in order to do that, we looked at a bunch of rules. There were 7 rules there. I'm not going to rewrite them all because basically that would just be redoing the video. But you've got all of these rules. Perhaps I should have mentioned, if you look in your study guide, you have the outline and all that kind of stuff as you normally have in the study guide. But in this study guide, there also is all of those rules written out for you. So take a look in there and then just do some practice. These take a little practice, but they're not too hard. So I hope you enjoy them. All right, and I'll be back again later. I look forward to seeing you in the next one. All right, thank you, everyone.